All right, so in 6.3, we're going to be talking about another way to find volumes. So last time we did the disk method and we did the washer method to help us find volumes of rotation. We discovered that some volumes were difficult to calculate or impossible using disks. Using either disks, that shouldn't be of shells, it should be or washers. Consider the solid obtained by rotating this curve, x equals 1 minus y minus 1.5 squared, about the x-axis. So as we talked about, in order to do this, if we're going to rotate about the x-axis down here, our approximating rectangle has to be perpendicular to the axis of rotation. Well, if we wanted to do this and rotate around that way, we're going to have a bit of a problem, because our upper curve and our lower curve are the same thing again. And when that happens, we have to do a bunch of messy algebra and actually find this maximum point, split it into two curves, two different ones with a plus or minus, and do a bunch of algebra. So that's where our idea comes by doing our volume by cylindrical shells. So the idea is, instead of going in the x direction, we're going to make our approximating rectangle in the y direction, and it's going to be delta y thick, and we want to rotate this about the x-axis. So imagine now we're trying to rotate this solid, and so we have something that looks like this, and we're going to have this distance right here. So I'm going to try to draw this as best I can. So this is our x value. So imagine we now have something that looks like this. So we would have a circle, and then we're going to have this. We're going to have something that looks like this. So imagine imagine a soda can with the top and the bottom cut off, right? So the aluminum's really, really thin, but it makes a ring, right, with a hollow center. So now what we're really doing is we're going to have this part right here is our thickness, delta y. The height of this is going to be our x coordinate. So then we're going to have something that looks like this, delta x, and then we're going to have our radius of this thing. So that would be, if we were rotating about this axis, our radius would be the distance from here to here. So what coordinate would that be? Well, that would be in this direction. That would be our y value, so that would be our distance from here to here would be our y. So this is the idea of a cylindrical shell. If I'm trying to rotate this curve about the x-axis, instead of thinking of rotating it, imagine making a whole bunch of these shells as cross-sections, starting from the y value here to the y value here. And if we had a whole bunch of these and then filled them all in on top of each other, that would make our three-dimensional solid, right? So this is similar to what we did in the pyramid example at the end last time, where we just made cross-sections. Well, instead of making cross-sections in the traditional sense, we're making these little cylindrical shells and then filling them out to find the volume. So let's do a little bit of geometry on this to see if we can figure out what its volume is going to be. So imagine now we take that soda can and we cut it down its lateral side and we lay it down flat. So if we did that, We're laying it down here. We know that this coordinate is going to be x. And then if we unrolled it, it is going to look something like this, because if you unroll a soda can and lay it out flat, it's going to make a rectangle, right? So we have something that looks like this. So we have our one dimension here. Let me make our slab. And we know that it's delta x thick. But then, how long is that thing going to be? Well, sorry. Our height, sorry, I need to rotate this. Our height is going to be x, so that's here. How long is this side of our thing going to be? Well, what is the distance around a circle? The circumference. And what's our formula for the circumference of a circle? 2 pi r, right? So if we look at our diagram here, it's going to be 2 pi r. So we're going to get something like that. But what's our radius? Y. So this is going to be 2 pi times the y value. So then what would our little piece of volume of that cylindrical shell be? Well, it's length times width times height. So then we're going to get our 2 pi y times x delta x. And that would be the volume of that little slice. So once again, if we take the limit as the number of slices go to infinity, we're going to end up with these two formulas. So our volume is going to be 2 pi y f of y dy, or v is equal to 2 pi x f of x dx. So notice, when we use our function of y, we are rotating around the x-axis. If we use a function of x, when doing cylindrical shells, we are rotating about the y-axis. So you might be looking at this formula and you're like, well, wait a minute. See, I did it again. That's a delta y. See, I'm making typos everywhere. Delta y. You might be wondering, well, how come we have an x in our formula here? Well, according to this, what is x as a function of y? The 1 minus y minus 1.5 squared. So when we think of this, x in this case is really f of y, and this is exactly the volume element for this, as we said, when rotating about the x-axis. If you did a similar picture, turned the can upright and went through the geometry, you would derive something equivalent for the other formula. So something that's going to be very important, in 6.2, we did volumes around the x and the y. When using discs and washers, the axis of rotation was perpendicular to the discs and the washers. When doing shells, the axis of rotation is parallel to the shells. So the distance that we're talking about, so you see our approximating rectangle here, is parallel to the x-axis. So note the approximating rectangle is parallel to the axis of rotation. If we look back at 6.2, when we did our discs or washers, if we look at our approximating rectangle in this example for the disc method, we're rotating about the x. With discs and washers, the approximating rectangle is perpendicular. So that will help us choose which method we are using. So if your approximating rectangle is perpendicular to an axis, you're using discs and shells, or discs and washers. And if it's parallel to the axis, like what we're seeing here, then you're using cylindrical shells. And that's how we're going to do the two different formulas. So that's really the key idea. Draw your approximating rectangle, and that will help us choose which method we're going to use. And you will get the same answer regardless of which method you use. Sometimes one will be much easier than the other, and we'll do some examples of that in a little bit. So let's go ahead and do example number 1. So sketch a cylindrical shell and find the volume obtained by rotating about the y-axis, the region bounded by y equals 2x squared minus x cubed, and y is equal to 0. All right. So let's start by drawing a picture of our curve. So we have 2x squared minus x cubed So we graph that, and it's above y equals 0. So let's zoom in a bit. So let's go x min -1. Let's go x max 4. We'll go with 0.5s, and then we're going to go our y min -1, y max 4, and then we can do 0.5s again. So we get something that looks like this. So first thing we want to check is, well, what is our goal? We want to rotate this about the y-axis, and we want to use cylindrical shells. So with cylindrical shells, we know our approximating rectangle needs to be parallel to the axis of rotation. So that means my approximating rectangle is going to look something like this. So then my shell would actually look something like this. For each of those, use your imagination because I'm a terrible artist. I'll try to sketch it over here. So it would look like something like this. That's a little better. Where this thickness right here would be our delta x. This is going to be our height, which is f of x. And then the distance from the y-axis to the approximating rectangle is going to be our radius for our circle, right? So then this distance right here would be our x, right? So that would be like our radius. And then imagine if we started at 0 and then just filled it in with a bunch of these shells, we're going to make a solid out of those shapes. All right, so now that we have our approximating rectangle and our cylindrical shell, we can find our limits of integration, and we get those by solving 2x squared minus x cubed equals 0. Using our eyeball metric here, it looks like it's going to be 2, but let's verify. So we factor out our x squared, and we get 2 minus x equals 0. So our solutions are 0 or x equals 2, as it looked from our graph. So now we want to use our formula for this. So rotating about the y-axis, our volume is going to be 2 pi x f of x. So our volume V is going to be the integral from 0 to 2 of 2 pi x f of x, and our f of x is 2x squared minus x cubed dx. So we pull our 2 pi out of our integral from 0 to 2 pi and then distribute our x in. So we get 2x cubed minus x to the 4th, and we find our antiderivative. So it's going to be, the antiderivative of x cubed is x to the 4th over 4. So we're going to get x to the 4th over 2, because the 2 and the 4 simplify, minus the antiderivative of x to the 4th is x to the 5th over 5. And then we evaluate that from 0 to 2. So we get 2 pi times 2 to the 4th over 2 minus 2 to the 5th over 5 minus, the other ones are going to be 0 and 0, so that's not going to contribute to our integral. 2 to the 4th is, well, 2 to the 3rd actually is going to be 8. 2 to the 5th is 32. Those are all 0 times 2 pi. And we probably should have just used our calculator because I don't trust myself anymore. So let's go with 8 minus 32 over 5. And we times that by 2. And we get 16 pi over 5. So cylindrical shells gives us a tool to rotate something about a different axis, which would be really hard. So it's worth noting, note, this is difficult with discs or washers. If we take our same picture that we had in our graph, and if we're trying to rotate this about the y-axis this time, if we want to use discs or washers, that's our approximating rectangle. So and so to be able to do that, you would actually have to find the maximum right here and break it into a couple of different integrals and integrate from there to there and then from upper to lower and upper lower. It makes it kind of a giant pain. I'm not saying it can't be done. So to correctly do it for discs or washers, you would actually have to do two different integrals like this. and integrate over the appropriate values when doing so. So once again, this would be, note that it's perpendicular. Whereas ours was parallel to the y-axis, which in this case made it a lot easier. So find the volume of the solid obtained by rotating about the y-axis the region between y equals x squared and y equals 2 minus x squared. All right, so let's start, as we always do, by drawing a picture. So let's go with y equals x squared and y equals 2 minus x squared. So I'm going to go zoom and 6 to get back to my standard window. So there's my region. So once again, I am going to zoom in. So let's just go zoom 2 and press enter to zoom in. See what we get. So our region looks something like this. So our goal is to find the volume of the solid by rotating this about the y-axis. And we need to add one more thing to this, and we really need x bigger than 0, because we don't want to rotate. This. So our region would be where it's bigger than x squared. So that's going to be over here, here, and here. So if we want to rotate this around the y-axis, if we tried to use disks, that means our approximating rectangle would look like this. We would need to calculate 2 different integrals. Because on this part right here, we would have, this would be our curve y. But on this piece down here, we would have a different y, right? So that would be like y1 and y2. And we would have to actually calculate 2 different integrals to do it that way. Whereas if we use shells, our approximating rectangle can be parallel to our axis. So then this would be our approximating rectangle. And we could do this by having our y1 and our y2. So here's our y1, and this guy is going to be our y2. So then the height h is y1 minus y2. Or in other words, we're going to have our 2 minus x squared, and we are going to take away from it our x squared. So now we're ready to do this as soon as we know our limits of integration. So we set our two curves equal to each other. 2 minus x squared is equal to x squared. And we add x squared, and we add x squared, and that gives us 2 equals 2x squared. Divide by 2, divide by 2, so we have x squared equals 1. Taking the square root, we get x equals plus or minus 1. So now, our limits of integration are going to be, so for our volume, we have the integral from 0 to 1 of 2 pi x times f of x, which is 2 minus x squared minus x squared dx. So collecting our like terms and pulling our constants out of the integral, we get 2 pi times the integral from 0 to 1 of x times 2 minus 2x squared dx. So distributing our x into our parentheses, we get 2x minus 2x cubed dx, giving us our antiderivative of x squared minus x to the 4th over 2. Don't forget our 2 pi, and then we evaluate that from 0 to 1, and that gives us 2 pi times 1 minus 1 over 2 gives us 2 pi times a half which is equal to pi. Looks like this. And we want to rotate this around the y-axis. As it turns out, you could use discs just as easily, or actually be washers, and get the same answer. So if we did our rectangle parallel to the y-axis, we're going to have that our height is going to be x minus x squared. And our intersection of these two curves, we set them equal. We have x equals x squared minus x, and we factor, so that's x and x minus 1. So our two solutions are x equals 0 or x equals to 1. So then our volume would be the integral from 0 to 1, 2 pi x, our height, or our f of x, in this case is x minus x squared dx. So we get 2 pi, the integral from 0 to 1 of x squared minus x cubed dx, 2 pi times x cubed over 3 minus x to the 4th over 4. And we evaluate that from 0 to 1, getting 2 pi times 1/3 minus 1/4. And so that would be 2 pi, common denominator would be 12, so 4 minus 3, giving us 2 pi over 12, or pi over 6. For our solution. And as always, that's all calculator food. You could just type it in without pi, and our calculator would do all the dirty work for us. So our next example we're going to work on is we're going to have to think back to Calc 1 a little bit, because we're asked to find this integral, and then we're asked to use the midpoint rule. And we'll discover when we get to the next chapter that we're going to have to do this more often than you would think. It turns out there are lots of functions that are either hard or impossible to integrate. So in first semester calculus, we kind of give you the idea that you can always find an integral or an antiderivative of something. Antiderivative, no. Integral, yes. But we may have to approximate. And I know that we've used those terms almost as synonyms. Indefinite integral is a synonym for antiderivative, but not integral in general. So let's go ahead and set up this integral and see what happens. So we want to use the midpoint rule with n equals 5 to estimate the volume obtained by rotating about the y-axis the region under the curve y equals the square root of 1 plus x cubed. So let's go ahead and draw our picture. We have the square root of 1 plus x cubed. We graph. And we get something that looks like that, and we're only worried about the values between 0 and 1. So we have our 0, we have our 1. We have this, and we wish to rotate it about the y-axis. So we wouldn't be able to use, in this case, if we tried to use disks, we would run into a problem out here when we would try to make our approximating rectangle again, where we'd have the upper and lower curve being the same thing. So our volume is going to be the integral from 0 to 1. We have our approximating rectangle going this way, so it's going to be 2 pi x times f of x. So that's going to be the square root of 1x cubed dx. So we want to integrate this, but as we mentioned, we could try a u substitution on the radicand, but the derivative of x cubed is 3x squared. Turns out that this does not have an elementary antiderivative. And if we don't know an antiderivative, we can't use the fundamental theorem of calculus part 2. Right? Because the fundamental theorem of calculus part 2 says if we know an antiderivative, the value of the integral is f of b minus f of a, where f is the antiderivative. So this is something we will resolve later on in this semester, especially in Chapter 11. We'll learn how to find integrals of almost every other kind of function. I'm going to say almost because There are still some things that will defy our integration, but if you keep going on, we'll learn how to integrate more and more things. So let's go ahead and do this using the midpoint rule. So remember, the idea of the midpoint rule is, let's look at our domain of integration. So here's our x, and we're integrating from 0 to 1, and the idea is we need to find the width of each of these. So we're going to use 5 approximating rectangles. So our delta x is always b minus a over n. So our limits of integration are 1 and 0. So it's 1 minus 0 over n, which is 5. So it's 1/5. That gives us our delta x. And then we find our sample points by finding the midpoints of each of these regions. So we would have 1/5, 2/5, 3/5, and 4/5. So then the points we're looking for are actually going to be here, 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 and here, right? So we can find a formula for those points, and we will call it x sub I is equal to, well, to get to that point, the midpoint is halfway in between one of those regions. So our formula for the midpoint for x sub I is going to be delta x divided by 2 plus delta x times I minus 1, as I goes from 1 to 5. So notice I set up this formula. You could set up another version that would be mathematically equivalent. X sub I equals delta x times I minus delta x over 2, as I goes from 0 to, or I goes from, well, sorry, I would still go from 1 to 5, as I goes from 1 to 5. And we would still get the same partition. So let's go ahead and do that for either one of these. So then our x sub I, I'm going to use the top formula. Our delta x is 1/5. So it's 1/5 divided by 2 plus our delta x, which is 1/5, times I minus 1. So 1/5 divided by 2 is 1/10 plus 1/5 I minus 1/5, which would then simplify. So that's 2/10 to 1/5 I minus 1/10, which is really just the long way to get the same thing you'd get if you use the other one. But the idea was we were trying to find these sample points, right? So to get halfway in between, what did we do? In the top formula up here, we started by adding half of the width of a rectangle, and then we kept adding delta x's to get to the next one. In this version down here, we started at this right here, but then immediately added a delta x. So we're getting, it's just two different ways to arrive at the same point, and if you simplify both of them, you get the same formula. So I'm just saying there's multiple ways to visualize the way these things get set up. So whichever way gets you there is the correct way to do it. So now we have our x sub I is 1/5 I minus 1/10, as our I goes from 1 to 5. So then remember, the integral from 0, or from a to b in general, of f of x dx is approximately equal to the Riemann sum. So the sum, as I goes from 1 to n, of f of x sub I times our delta x. So we've calculated all of these parts, so we're going to plug them into our formula. So we have the sum, as I goes from 1 to 5, of f evaluated at x sub I. So f is our original function that we have right here. So this right here is our f. So we have 2 pi x. So 2 pi x sub I times the square root of 1 plus our x sub I cubed times our dx, or our delta x. And our delta x, well, I'll leave it in red for now. Now we plug those in to finally get the sum, as I goes from 1 to 5, of 2 pi, and then our x sub I is the 1 over 5 times I minus 1/10 times the square root of 1 plus 1 over 5I minus 1/10 cubed times our delta x, and our delta x was what we found all the way up here. Delta x is 1/5. So finally, pulling our constants out of the sum, so 2 times pi times 1 is 2 pi over 5. Clean this up just a little bit. I equals 1 to 5 of 1 over 5 I minus 1/10 times the square root of 1 plus 1 over 5I minus 1/10 cubed. And we now need to calculate that sum, for which we're going to use our graphing calculator. So this is how we would formally write it out. But let's talk about how we can use our calculator to simplify this process. So the first thing we want to note is to use our calculator. Let's go back and put our f of x in to our calculator. So our calculator, we're going to go to y1, and we have to put in this whole thing, so 2 pi x, and we're going to square root 1 plus x cubed. So we've got this thing in our calculator, and what we really want to evaluate is this sum. So to use our calculator, so 1, we're going to put f of x in y1, which we already did. So then, step 2, we're going to use the Riemann sum formula, which is the sum as I goes from 1 to n of f of x sub I, but our x sub I in this case we need to write out explicitly. So it's going to be f of 1/5 I minus 1/10 times delta x. And this is what we're going to put into our calculator. So we've got our function in. So remember, to get sigma on our calculator, we press alpha and window, and we choose choice number 2. So that's alpha, window, and choice number 2. So we go down to number 2. We have our sigma, and we're going to put in our I. So I is going to go from 1 to 5. And then we get down inside our parentheses. To get our y1, we go alpha trace. We select y1. And now we put in our delta x, which is going to be 1/5 times I minus 1/10 and we go parenthesis times our delta x, which is 1/5. And we hit enter on our calculator, and we get that as our sum. So it is worth noting once again, if you typed this monstrosity into your calculator, you will get the same thing. You just really don't want to do that. So it's a lot easier to put the function that you're trying to integrate in as y1, and then you just evaluate it at the x sub I and multiply by delta x and have it do the sum for you. I make a lot less typos if I do it that way. I'm not saying you can't type it in directly just like it did up here, and if you